Swayam Prabha. Digital India. Educated India.
Now that we have discussed all the passives that we'll need or use for millimeter wave IC design, so let's start building arrays and we've also seen that in millimeter wave ICs, usually in order to meet the link budget, we are building arrays. We're not building single elements, right? So we'll begin by just discussing architectures for arrays themselves. And if you do intend to, ever build a single element transceiver, you just don't use all the signal distribution components in there, right? So we saw that the approximation that we were making was that we were taking the variable delay and we were approximating it with a phase shifter, right? We also saw that we need variable gain in order to control beam nulls and beam patterns. So those are the sort of built-in blocks that we need. But the question becomes, now that I want a phase shift, where do I implement the phase shift, right? And this is again a benefit of integration. I can do the phase shifting in the RF path, right? So the signal comes in, considering a simple 2-element array, the signal is coming in from a direction, seeing an extra phase shift in another path, adding up coherently. I'm multiplying it with the LO and it is coming down to IF, right? So all the phase shifting is happening at RF, but the key here is that the phase shifter is in the signal path, right? So since the phase shifter is in the signal path, all the things that I worry about signal path components such as noise, linearity, right, matter. So now I have to design the phase shifter considering these. And also importantly, if I'm interested in wideband arrays, then I have to consider the bandwidth of the phase shifter because it's operating across the entire RF frequency. We are showing a receiver, but the same is true for the transmitter as well. So I have to worry about the bandwidth over which the phase shifter is operating, right? So this makes the phase shifter design more challenging. But if I'm able to accomplish this design, then I've certainly made the rest of my signal path quite simple because I don't have to send any other signal to all the elements. Beyond this part, it just looks like a traditional receiver that I have to design. So it's a lot easier for me to do this. So this kind of approach leads to typically overall quite small area, right? But I have to always worry about the phase shifter performance. And in particular, we should also add another metric here, which is phase shifter loss or gain, right? Because if the phase shifter has a lot of loss in this system, then it may not be protecting the subsequent blocks' noise in my cascaded noise figure. So I have to design my phase shifter to have an acceptable loss at that frequency, right? So let's say that I do find RF phase shifters to be difficult at that particular frequency. And over time, that frequency has been pushed higher and higher, but still there are some high frequencies at which RF phase shifters are difficult to implement. Then I can take the advantage of integration and down convert the signal in each element, build myself a heterodyne architecture, right? And then I have as many IF paths as I have a number of elements. And in the IF path, I implement the phase shifter. So all the things that we said about the phase shifter are still true. It's operating at in the signal path, so I need to worry about noise, linearity, all those things. But it is occurring earlier in the signal chain for the transmitter, later in the signal chain for the receiver, right? So the noise design is relaxed, the linearity design is relaxed. And also if I'm using the heterodyne principle, where as my omega RF changes, my omega LO also changes to keep my omega IF constant, then I'm basically creating a situation where my phase shifter has to operate over a much narrow bandwidth. So it's a lot easier to design, right? But the trade-off that I have is now I have created a full signal chain in each for each of my array elements, and I have to distribute the LO, which can be a high frequency signal, to all my elements. So now I need to create an infrastructure to be able to distribute this LO signal to all the elements, which can be challenging and area intensive. So RF and IF path phase shifting are equivalent, right, in terms of the phase shifter being in the signal path. But I can choose to move the phase shifter outside the signal path itself and then say that I'll implement the phase shift in the LO, right. So because then every time there'll be a cos omega RFT, this will get multiplied by cos omega LOT minus theta. So this will give me a cos omega IFT minus theta, right. So I am now able to translate a relative phase difference between the LO path into the IF path. And what is advantageous is that the phase shifter now, it's operating on a single tone, right? Or maybe varying or across tuning range, right? But its instantaneous bandwidth needs to be it can be pretty low, because instantaneously it's only operating at the LO tone, and its noise and linearity performance is not as critical. Maybe the loss is important, because then I'm losing LO power, then I need to amplify the LO back again for the mixer. So loss may be important, right? But in terms of phase shifter design, this is relaxed, right? And I can also have architectures where in my mixer, instead of this, there is a multiplier, right? And then the phase shifter is before the multiplier, right? So that means basically that if I implement a phase shift of theta, I will see a m times theta phase shift at my LO. So now I'm even reducing the phase shifter range that I need to have. So instead of 0 to 360, let's say my multiplication ratio is 2, I only need to do 0 to 180, because the phase shift is going to get multiplied. So this makes my life easy as well, right? And but overall, the trade-off still remains that now I have a situation where I have to distribute my LO signal, and then I also have these multiple IF signals that are coming in. So I have n LO signals to deal with and n IF signals to deal with. And from an array perspective, this can take up area as well. The mixers, LO buffers, LO distribution, all that takes area compared to RF path phase shifting. The final holy grail in all this is to say that don't implement any phase shifters, don't worry about it. We will do everything in the digital domain, right? So I'm showing the RX, but the TX, the DAC would implement the phase shift in the digital domain. And then the signal just works as a conventional transceiver. So you have an array of conventional transceivers that are operating of a coherent LO, right? So as long as you're able to maintain the same coherent LO to all of them, then the signals in the digital domain, you can implement the phase shift, right? And this is really powerful, because in all the other architectures where we are combining the signal in IF, we are basically getting signals from one particular direction and adding it up, right? But in the digital domain, we have not made that decision until the digital. So we can basically, instead of making one beam, we can have multiple beams. We can add in the digital domain signals with different phase shifts and be able to look at multiple beams at the same time. So this is sort of the holy grail that everybody would like to get to, right? And there has been a lot of progress over the last few years in getting to these arrays. You can think of this effectively as a MIMO array, right? And if you think about the phased array, if you think about a phased array Rx, right? It is a multiple input, single output, or a multiple input, few outputs system, right? That's what it is. Whereas this digital beamforming, right, is a multiple input, multiple output system in theory. So it can be very advantageous if they can be implemented. right? So what is gating these digital arrays is basically ADC power consumption, but ADC power consumption does scale very well with advances in technology. So what is happening is that you're getting this sort of partition where the ADCs and DATs and the digital beamformers are being implemented in advanced technology, digital technology nodes, while you have signal chains that are being implemented in RF compatible technology nodes, and then we have digital beamforming arrays. So this is the way your FR1 base stations work, right? And going forward, there is a lot of desire to make millimeter wave work like this as well. So there is one particular disadvantage to digital beamforming arrays, right, which is in terms of dynamic range, right? So if we consider a world where there is a interferer coming from this direction, which I want to reject, right? In this particular approach, if I think about my desired signal, if I think about my desired signal over here and my undesirable interferer over here, right? Right? What is going to happen is that my undesired signal is going to be there on every ADC. There is no spatial filtering that has occurred, right? So my ADC dynamic range is quite high. Whereas I can over here, if that undesirable signal is coming here and I have formed a null, right? So what has effectively happened because of array combining is my desired signal has gotten stronger and my undesired signal has gotten weaker, right? So my subsequent ADC can be lower dynamic range. So the one disadvantage here is that if you want to deal in a situation where there are interferers, you're increasing the required ADC dynamic range compared to the other approach. So that increases power consumption. And of course, all the other caveats about larger area because you have larger signal chains, right? And larger power consumption because you have both digitization and signal chains and LO distribution. Because here the power consumption is just literally going to scale as n times your signal. Sure, but I mean, if you are generating an RF DAT in even an LO array, right? Even in a RF phase shifting array, whatever the DAT puts out, the DAT puts out, right? So it is true that we create some nulls in certain directions, but effectively, if the DAT has some spurious tones just from an TH perspective, right? Let's say that my DAT is my TX has inbuilt some spurious tones generation, and I have a phased array, right? Then no matter what direction I go to, it might be true that in some directions I get a strong signal, right? But the relative ratio of the two will still be the same, right? So the phased array is not, and in another direction I might be generating a null. So I might have a weaker signal, but then I'll have a weaker spur as well. But relative to each other, the delta is always going to stay the same. So this is not providing any more filtering than that does. I mean, if the offset is big enough, then maybe there is some frequency dependent pattern in the array, so things change. But you can't really count on that from a system perspective. That's quite complex. So it is really a question of dynamic range and power consumption. So let's talk about then the key building blocks that we have in an array, right? So low noise amplifiers and power amplifiers will do next because they are sort of common to all millimeter wave transceivers. But the effective blocks that we are adding because we have built a phased array are phase shifters, variable attenuators, and signal combining, right? So we'll go over topologies for phase shifters and topologies for attenuators and combiners that we use at millimeter wave, right? So the first question is, okay, how much phase shifter range and resolution do I need, right? If we ask ourselves, let's say that we have an array that is So let's make an array that has n elements, right? And the spacing between the elements is d, right? And we know that basically the theta that we need to provide depends upon the angle of incidence, right? And if we assume just in the simple case that d is lambda over 2, right? The theta that we need is pi sine phi, right? So we have seen that. So let's say now that this phi I implement with an n-bit phase shifter, right? So across the array then I have for a given phi naught, right? I basically need to implement let's say 0, theta, so on and so forth, and then I have n minus 1 theta, right? This is the phase shift that I am providing, right? So since I am implementing only an n-bit phase shifter, each of these wants a certain phase, and I will be making a slight quantization error because my phase shifter only has some finite resolution, right? So if I think about it that way, I can think that I am supposed to receive from some angle, but because my phase shift is quantized, I'm actually going to have a slight error in the angle that I'm receiving from, right? And we call that beam pointing error, right? And to sort of approximate it in one way, what we can think of is, let's consider that I have just a 2-element array, right? And in that, but the 2 elements that I have are 0 and this element over here, right? Which is the whole size of my array, right? And given this scenario, right, I basically know that in order to receive from particular angle, right, I have theta is pi sine phi, or in this particular case, I need a phase shift of n times theta, right? So that's basically what I need. So you can think that if I move my, let's say that the minimum resolution that I have is theta res, right? That's the minimum resolution that I can implement. Then the minimum change in phi that I can observe, right, is basically sine inverse theta over theta res divided by pi times n. So this basically corresponds loosely to an array in which the let's say that I was receiving it at 0 and I change the angle slightly where things are coming from, right? Now this needs a very small change in theta which is below my resolution. So I just round it to 0, right? And I have 0, 0, 0 for half my array. And for the rest of the array, I have theta res, theta res, theta res, theta res, right? So I basically, half my array is at 0, half my array is at my first bit. Some rounding error like that. I basically get a beam pointing error that looks theta res divided by pi times n, right? So what this is basically saying is that my beam pointing error goes down as I increase the number of elements in my array. As you can imagine, if I have a very large array, right, then these approximation errors are going to sort of get averaged out as I keep rounding every element to the nearest phase that I can get, right? So you, and of course, if you reduce your theta resolution, you can reduce this beam pointing error, right? So from a mathematical perspective, if we just make a plot, what we can see, for example, is that let's say I have 2 bits resolution and I have a desired phase shift that looks like this, right? Then as my desired phase shift that I want changes, right, and I have 2 bits resolution, I'm basically rounding it to the nearest phase that I have. In 2 bits, for example, I have 4 levels, right? So I have 0, 90, 180, 360. So there will be a point where I'll have a peak error of 45 degrees, and then the error will start falling, right? So you can see that basically the error in theta keeps obviously reducing as you increase the number of bits, but and then you can use that theta resolution that you have and apply that for arrays of different number of elements. So shown here is a 4-bit and 4-bit and 6-bit resolution, right? And this is the beam pointing error that you get, right? So you can see that for a 4-bit resolution, the beam pointing error even for a pretty small array is only 1.8 degrees, right? And then as you gradually increase the number of elements, you find that the beam pointing error is falling quite steeply. And then with 6 bits, the beam pointing error is only of the order of half a degree or less than a fraction of a degree, right? And this is actually much smaller than my half power beam width. So from a beam pointing perspective, phase shifter quantization doesn't really impact me, right? So the beam pointing error is quite forgiving of phase shifter quantization. But where I really find a problem is in what we call quantization side lobes. Because in order for two signals to cancel at my nulls, for example, and in order for signal cancellation that brings my side lobe levels down, right, I need phases to be aligned. But when the phases are slightly misaligned, even within the resolution, then the residual amplitude shoots up, right? So I can basically have a metric where I see, okay, how, what is the quantization, peak to side lobe or peak to worst case null level sort of error that happens. And what I find is that error gets impacted by phase shift resolution. So, but even that error goes down quite a bit when you increase number of elements in the array. So what you can see here is quantization side lobe levels, right, as a function of the number of bits in the array and the number of elements that are there in the array, right? And you can also see that as I go from 2-bit to 3-bit to 4-bit, 4-bit to 5-bit, basically it is dropping by 6 dB, right? This is similar to the ADC quantization, where every time you add an ADC quantization bit, your quantization errors or quantization noise drops by 6 dB, right? There's a one-to-one mathematical analogy between that kind of reduction and here. And what we can see is that, let's say that I do some kind of Taylor weighting, for example, to get my side lobe levels down to minus 30 dB, right? Then I will find that I need to at least use a 4-bit phase shifter if I'm using a small element array, right? If I'm using a larger number of elements array, I can live with a coarser phase shift. But this is what basically sets your side lobe patterns. Nulling or quantization side lobes is what sets your phase shifter resolution, not your beam pointing error, because that is pretty forgiving of phase shift errors. So in integrated implementations, we operate in this sort of region, right? Because it's possible for us to get 4 to 5 bits error reasonably. 6-bit is also feasible. It also depends on how you quantify your error. Are you quantifying it as the RMS error across phase, or are you quantifying it in terms of the maths error that you have across your phase shifter resolution, right? So 6 bits of phase is already like 64 levels, right? So that is 5.625 degrees of phase resolution, which across process and corner is a good challenging number to achieve, particularly if you are trying to have your phase shifter setting be the same across frequency. So these kind of numbers are what we typically target in integrated implementations. If you think this way, right, let's say that your array number of elements is increasing. That means the spacing between your first and last element is increasing, right? I can do 0 degrees here and I can do theta res over here. But this spacing is now n minus 1 times d, right? So if I think about a particular angle where the signal is coming in from, right? I'm basically my the theta difference that I get between these, right? It's n minus 1 times d times sine phi over c, right? That is the time difference, and I have to divide that by the one this divided by the time period or multiplied by the frequency, right? So let's say d is lambda over 2. So then you basically have a situation where you can receive a very small change in shift because your baseline has increased a lot, right? So this is why when your number of elements increases, your resolution of beam pointing increases, and then since now there are more elements in the array, the quantization noise is distributed across the array, right? So as a result of that, you'll basically get side lobe patterns that go down, and so you'll be able to get better lower side lobe quantization side lobes for the same phase resolution. And these type of arrays, 100 to 1000 is, we are building those in integrated implementations all the time. So if we are operating in this region, you can see that we are living with quantization side lobes that are in this space, right? 4-bit to 6-bit space. So this is more than what Taylor itself achieves. So just I'm now limited by my amplitude weighting quantization rather than my phase quantization. So now that we are trying to target, let's say, a few bits of resolution on phase shifters, right? So we can, what all do we need from it? So the first thing we need from it is range, right? We need it to go 0 to 360 degrees. So I'll move to degree notation here instead of 2 pi radians notation, right? So 360 degrees here. We need to worry about its insertion loss or gain, right? We need to make sure that the gain is uniform across the phase shift, because ideally we'd like something where if I were to make a plot of the phase shift that it is providing and the gain of the phase shifter, gain or loss, right? I'd like to have a straight line, because all my algorithms are assuming that my amplitude and phase are orthogonal to each other, right? So I ideally like this, right? I want to have good resolution, right? So 4 to 6 bits maybe, right? I want to have good bandwidth, right? Because as I am operating at different f0, I would still like to know that two paths are 90 degrees apart, for example. So I would like 90 degrees phase at whatever the f0 that I'm operating at, which is of interest for that application, right? But this gets a little complicated from a system perspective, because remember, we are approximating the delay with the phase shift, right? So given beam squint performance and all that, this becomes something that you often have to feed into the system to see what your pattern looks like. So this is a little complicated. There is noise, there is linearity, right? there is area and power, right? Because we have n of these. So the area and power quickly add up in an array, right? There is PVT variation because we don't want to calibrate every phase shifter during test, right? So it should give the same phase as we for every element and across every multiple ICs, right? But we often also we care about relative phase, so we care about the phase shift difference between states because that's what different elements will be at, right? So we worry about that. Then there is a secondary concern which is response speed, that basically it should change very quickly, right? But this is usually not a concern for phase shift integrated phase shifter applications because there is the time constants that are on chip for changing phase shift are never really an issue in integrated designs, right? So overall, we have broadly two approaches, right? We can think about active phase shifters, right, or passive phase shifters. And nothing is stopping us from combining different kinds of phase shifters into our system and just build hybrid phase shifters in our design, right? We can use, so what we are going to do is discuss some individual phase shifter building blocks. You can mix and match them inside your implementation quite freely. So so we'll basically discuss in passive phase shifters first, right? We'll discuss switch type, reflection type, right? And then we'll basically do a variable T-line type as well, right? So broadly, what is a switch type phase shifter? So this at its simplest, you can think about a port here and a switch, right? And one path over here, right, maybe has an extra delay. And one path over here maybe looks like this, right? So I can choose whether my phase shifter goes, my switch is turned this way or this way, right? I can basically choose to go from input to output through this path or this path, right? So this is one type of phase shifter. You can clearly see that if I build this using transmission lines, there are area implications and things like that, right? So we won't really look at transmission line based phase shifters, right? But you can approximate this, for example, through pi sections and things like that. So broadly speaking, you effectively have some switches that are changing the path through this approach. So the benefits of this are that it is passive, right? Passive, so it's linear, low power, right, or zero power. So these are the benefits, right? The disadvantages are that it can be lossy, it can have a large area, right? And we have usually a resolution trade-off, right? Because it basically needs one of these sections, right? Needs one section for every bit, right? So if I have a multi-bit design, if I call this one STPS, so there has to be an STPS that maybe does 0 or 180 degrees switch. Then another STPS that does 0 or 90 degrees, right? Another STPS that then does 0 or 45 degrees, one that gets to 0, 22.5 degrees, right? So now I've got myself a 5-bit phase shifter, right? So these are controlled by the bits that are, but you can see clearly that, you can clearly see that as I keep increasing resolution, I'm keeping on adding blots. But it is also true that the larger the relative phase shift, usually the larger the area of the blot, the 0-180 phase shifter is going to be bigger than the 0-11.25 degree phase shifter. So as you go down the resolution chain, the phase shifter, switch type phase shifter is getting smaller as well, right? So that's practical. So what is inside these blots if I am trying to build a phase shifter? So you can build a pi type phase shifter, right? A pi type switch type phase shifter. So essentially the circuit looks like so, right? So you have C1, C1, and then you have a switch here, and then an inductor which is, let's call this L switch, right? And actually maybe it's better to call it L1 because okay, yeah. So this switch over here, and then we have okay, we are basically this is a switch over here, right? And we have an inductor over here, which is L1, right? So we are going to call this V control, and we are going to call this V control bar, right? And let's call this L switch here. I think that's fine. So there are two states to this, right? So V control is 1. This network looks like this is R on, right? And then you have L1 up here across here. You have C1. But this switch is off, right? So what you have is C off, and you have L switch, right? So this is what this looks like. So in this situation, let's say that we design L switch to be 1 over omega naught squared C off, right? So what's going to happen in this case is that this resonates, right? So your impedance looking over here is high, right? So you have a high impedance there. So you effectively have L1 and C1 divided by, so you're basically, you have the network that looks something like this. R on, L1, right? And then you have C1 in series with C1, so C1 over 2, right? But this is what your network looks like. Let's say it's dominated by R on being very small, right? So the signal is going to go through. And then in the case where you have Vc equal to 0, right? So this switch is on. So at that point, you have L1, you have C1, you have C1, and then this switch is on, right? So this is an R on, and the inductor is in parallel with it, but we can ignore it because it is its impedance is going to be higher than the switch. So in this scenario, this is a pi section, right? And we can consider this port 1, port 2, right? And if we want to get a certain phase shift theta between them, right? So you can design, and at a certain impedance, then this is L1, Z naught sine theta by omega naught, right? And then your C1 is tan theta divided by 2 divided by omega naught Z naught, right? So if you build this, right, for a particular phase shift that you'd like, right, you can assume that between these two states, the relative phase shift is theta, and when it is in the VC0 state, this section has an impedance Z naught, right? So when you are cascading multiple phase shifters, right, every phase shifter is basically still has a impedance Z naught, right? So you can connect, you can easily wire interconnects between them, which are transmission lines of impedance Z naught, right? So that way your loading impedance and all that works out, and so you're able to build a cascaded series of phase shifters by implementing such a system. So you can look at the inaccuracies of the model that we are doing, right? So over here, for example, you have a L1 R on C1 over 2, right? So you do have a resonant circuit here at that particular frequency, right? So that's one thing. And then you have this R on, and this is basically, if I look at it from a previous stage perspective, right? Let's say that this is R on, and then you have Z naught here, right? Then over here I see Z naught plus R on, right? So I am getting mismatches as I go through these states. That's going to happen. So that's one thing, right? There are some experiment. Okay, I'll come back to that in a second. But the switch design itself, right? So if you consider a CMOS switch, right, R on is proportional to 1 over W of the switch, right? And C off is proportional to W of the switch. So you end up with a R on C off, yeah, is a constant, right? Constant for the technology, right? So basically this is actually called exactly that. It's called the switch time constant, right? And it's of the order of hundreds of femtoseconds for CMOS, right? So you can, let's say 200 femtoseconds for, but I mean, there are SOI technologies which basically are, claiming to be in the 100 femtosecond range or sub 100 femtosecond range. But, when you start doing layout and you see all the degradations of the wiring and all that, these sort of numbers are reasonable to assume, right? So if you have something like this, then you do have a trade-off between R on and C off, right? So that's why you have this component here, because this lets you increase this more so that you can have a very low R on in the VC equal to 0 state and not see an impact of this in the LSW state, right? But in practice, if you make your C off very large, right, your LSW decreases. So Q times omega times LSW decreases, right? So this basically means that your effective RP decreases. So this assumption over here that this is an open, right, fails, because this is actually RP when it resonates, right? So then you actually have a network, an RC network that is sucking some signal in, right? And that again causes both mismatch and a delta in the phase that is different from what you expect. So those are the practical joys of implementing this at millimeter wave, right? If you don't want to put buffers, there is some stuff that people have do where they, this is all though a little experimental, where they make the phase shifter and then there is a transmission line of a certain Z and certain L, and then there is a next phase shifter, right? And this basically shields this phase shifter a little bit from the impedance variations of that phase shifter bit. So that makes things somewhat more uniform, right? But at its core, that is the practicality of it. That's why you have finite bits, right? So if you want to get several bits, then the right approach is to put 2 bits together, make a buffer, put 2 more bits, make a buffer, put 2 more bits. That's basically the right approach. That is a solvable problem by increasing the number of pi sections that you have. You don't need to put the switch also again, right? So instead of having 1 pi section, I can make 2 pi sections, right, or 3 pi sections, right? And then have a switch that decides between this path and maybe something that is just going through, right? That works as well. Though typically what you will try to do is maintain some symmetry between the paths, right? So you'll make this low pass and you'll make the other section high pass. So you'll do something like this, right? And this will be the, so one is giving you a phase lead, another is giving you a phase lag. So you are able to basically get some, because otherwise this path will be lossy, this path will not have any loss. So then you have that gain uniformity issue across phase shifter bits. Right. So you try to make both paths equally lossy, not just have one path that is clean. So we considered pi type, right? But there is also T type, bridged T type. I'm not going to get into each of those, right? But just to give you a flavor of it, you can replace the inductances and capacitance, right? So you can have a T type where there is a switch, there is L1, L1, and then now you have another switch here, right? And then you have another switch here just to get the resonance under control, though you can maybe live without some of these switches, but this is from a particular implementation, right? So this is VC, this is VC, and this is VC, right? And in this case, when so VC bar, when VC is equal to 1, right, then that particular path is on, and then you have these inductances that are joined together, right? But you are basically trying to then enable this and get a resonance out here, right? So you're trying to resonate this. Right? And in the BC, yeah, so in the VC equal to 0 state, right? Then you're basically getting L1, L1, and then there is the off-state capacitance of this transistor, right? So that's giving you that C, and then this is on, so this is basically turning on R on. So you have a LCL section here. So again, you're basically this one goes through, right, and this one goes through this extra delay, extra phase shift that is happening over in this path. So overall, this is the broad flavor of what is done. But just to also highlight one thing in terms of implementation, right? So, for example, in the paper that I'm showing now, in order to implement the smallest phase shifter, right? In that case, it was a 5-degree phase shifter. They basically just have a switch, right, and an inductor, right? So when the switch is on, this is just a resistance, right? And when the switch is off, you are basically seeing C off, but you're seeing the CP of the switch to ground, right? And you're seeing this inductance, right? And that is enough to basically give you a 5-degree delta between the two states, right? So the components that you would need to build the whole pi section turn out to be small, that you can't accommodate a switch inside that. So you use the switch itself to give you the parasitics that you need for the section that you have. This is a implementation at 28 gigahertz, right? And they are doing what we discussed, which is they put a phase shifter, they buffer the phase shifter in between stages, right? And one of the things that they also do in this case is that this is if I think about it in terms of losses, right? So loss is decreasing as you go across from the high bits to the low bits, high delta theta to the low delta theta, right? So they consider as an approach where they put all the amplification up front before the switch type phase shifters, right? And that is fine, you get good noise figure, but then your linearity gets poor because the signal is very, very large here and then gets attenuated through this. So what they did was they experimented with different combinations of placing switches at different locations and the amplifiers at different locations, and then came up with this approach where they're able to balance the noise figure and linearity, right? And you can see that the phase shifters are also ordered differently, right? Partly for those reasons which you were talking about, right? This 180 is a big change, 90 is a big change. So instead of cascading the 180 and 90, you move the 90 here and you move the 180 here, right? So you are protecting the bit stages that have big changes from each other through phase shifter, through buffers, right? And this is basically a reasonable trade-off, right? But it's a system level trade-off that you've got to make on a case-by-case basis. These are not buffers, I should say that they're amplifiers, but yeah. Yeah, they implement their variable gain through implemented VGAs in this particular case. You need the variable gain in each element, right? So this is the VGA that is providing the variable gain as well. Yeah, instead you use an active amplifier. Putting it in between so that it helps the other way around. So it's this is again part of the reason to design things matched, right? Because if I design things matched, I can experiment with these orders, right? If everything has the same characteristic impedance, doesn't have to be 50, it can be 60, whatever. But then the other thing is that I like to test breakouts of these. So if I'm trying to test breakouts, better to design for 50 so that my breakout test is simplified, right? So then I just end up with everything on my chip looking like 50 ohm matched input and output networks. I mean, they have, just to show the measurements here, right? So you see some behavior that, for example, you can see that there is a gap that you can see across the phases on some of the bits, right? But if you take the overall phase shifter loss and resolution, people are getting in the 4-bit, 5-bit range, but you can see that the losses are quite high. Yeah, so this is one type of phase shifter, right? And again, implementations have been done, up to pretty high frequencies. But the key here is that the more resolution you add, you typically add more loss, right? And you can see this plus minus 2.1 dB means that in between your worst gain state and your best gain state, you have 4.2 dB difference, right? So this is something from a system perspective that you have to equalize somewhere else, right? So that is, maybe your VGA has to equalize for this, but it's just there. And also typically the RMS error that you look across phases is typically quite low, right? It's the maths phase error that is typically high. The RMS, because most of your states will be good, and then you'll find one state that, or a few states that give you a large error. So good to keep a track of both maths error and RMS error, or the equivalent to the ADC would be to INL and DNL. So you keep track of both of them. So this is the broadly switch type phase shifter. So you can put whatever networks that you want in between the two paths, right? That's done. The other broad kind of phase shifter is the reflection type phase shifter. And here, again, you could cascade multiple reflection phase shifters, right? But basically, the idea here is to use a quadrature coupler, which has this property that as long as both through and coupled port see the same termination, right? Then at the input port and output port, you are matched. So if you leave these open, you are matched. If you leave these both short, you are matched. As long as they are terminated in the same load, you are matched. And what you can show basically is that the signal from input to output, right? It basically depends upon the reflection coefficient of this load, right? So gamma t is zt minus z naught by zt plus z naught, right? So if you are able to vary this load, right, then typically when you vary a load, you change the match, right? Because if I just directly did this, if I try to attach this to my output, when I change the load, I'd be changing the match. But in this case, you change the this gamma t, but you are still keeping your input and output matched. The only thing that's happening is that from input to output, you are getting a phase shift that is controlled by that reflection coefficient. So now the first step is to design a quadrature coupler, right? And we have seen different kinds of quadrature couplers already, lumped, land, hybrid. All of those work, right? But you want a wideband coupler typically. So land is, for example, a very good option when designing this at really high millimeter wave frequencies, right? And then the objective becomes how to design this load, right? Because what you can see here is that there is the signal, the magnitude of the loss is also the magnitude of gamma t, right? And the angle, the phase shift that you are getting is just angle of gamma t plus, minus 90 degrees plus angle of gamma t, right? So what the best case scenario that would happen is somehow I could magically create a load that moved all the way around the Smith chart's boundary like this, right? Because this basically has a magnitude of gamma t equal to 1, and angle of gamma t is varying from 0 degrees to 360 degrees, right? And if I'm able to do that, then basically I'll put these loads on the other side of my hybrid coupler on the through and couple ports, and I'll get a full 360 degree variable phase shifter with uniform loss. Now, developing such a network is quite challenging, right? Because even if I take an ideal varactor, right? So an ideal varactor, if it has zero capacitance when I start, right? And then has extremely large capacitance when in its highest state, it can basically go from an open to a short, right? So a single varactor load can only do half the Smith chart. but a practical varactor only does from here to here, right? So if that means my phase shift range is only going to be from here to here, right? It won't even be 180 degrees, where I want something that is 360 degrees. So one way to think about it is that I want to synthesize loads, the terminations, which let's say I decide that I'm okay with 5 dB loss, right? So I've decided that the minimum, that gamma t min, right, is 5 dB, minus 5 dB, right? I'm willing to accept that much loss. So I can draw this circle on the Smith chart and decide that my load should never be inside this region, right? But I should try to see if I can vary my load inside in this region of the Smith chart. Can I synthesize all these loads over there, right? So as we noticed, just having a single varactor is only going to move us from one small section of the Smith chart, right? So we can then try to synthesize higher order loads, where instead of using just a single varactor, we use a CLC network. We vary C1 and C2, right? Because ideally, if you had a transmission line, right, and this transmission line, you could vary its effective length from 0 to 360 degrees, that would serve as a termination as well. That would also work. So you're trying to synthesize something that looks like that by varying C1 and C2, right? We can basically come up with equations for these load terminations, right? But actually maybe we can skip, yeah, it's, I'll just sort of write it here to show that with this higher order network, right, you can right? So what you're making is C2 variable, you're making C1 variable and this variable, right? So by varying these terminations, what you can then do is look at all the points that you are getting on the imaginary and real part. And again, what you want is full coverage around this region, but never something inside this region to avoid losses, right? And with this approach, or just broad design approach, both my group and other groups have demonstrated reflection type phase shifters. One other caveat to note, which is a little bit of non-ideality, is that while your coupler, the input and isolated port are supposed to be perfectly isolated, what you really have is a leakage signal that is always present. And then you have the signal that is getting reflected, coming back, getting reflected, coming back, right? So you have these three signals that are sort of adding up. And in a situation where these two are in phase, but if that is out of phase with this reflected signal, you will see a lot of loss, right? So then you can try to choose regions of the termination so that you are trying to avoid this leakage signal. And with those sort of design principles, so this is an example implementation at 94 gigahertz. So at this really high frequency, because of all the parasitates that are there, it's hard to get full 180 degrees, full 360 degrees phase shift. So what we targeted here was, okay, we'll get 180 degrees of variable phase from this reflection type phase shifter, and we'll get another 180 degrees through some other means, right? Maybe a switch type phase shifter. So you can combine these approaches. And what you see here is an example of measured performance. So you can get 5 bits, right, of phase, and that with about 7.5 dB loss, right, with reasonable loss uniformity across these states by varying C1 and C2. We also had an implementation at 28 gigahertz, and at 28 gigahertz you can come up with some tricks to increase that Smith chart coverage because the parasitates are lower. So with that particular example over here, right, with all the loads, what we end up seeing is that you can get to 330 degrees, right, over here, but then you can start doing approaches where you change this termination differently from this termination. And when we do that, what we do is we lose the matching property over here, right? So we are introducing mismatch in the signal. But if I'm able to live with a certain mismatch, I can cover the full 360-degree range. So 180 degrees is typically very comfortable to achieve with this reflection type phase shifter. So people have demonstrated phase shifters all the way from 20 gigahertz to beyond 100 gigahertz with 180 degrees phase variation with different network loads. So that's very feasible. Going all the way to 360 with one phase shifter is very challenging. So what we end up doing is combining this with some other phase shifters to get a full 360 degree during range. So if you switch between an open and a short, right, it is true that you can get there, but the problem is that in order to get all the midpoints, right, you have to vary. So physically, how do you switch between an open and a short, right? You have to find some way, okay, you put a short right at the termination, right? You put an open at the termination. But the problem is that there is some off-state capacitance and on-state resistance, right? But what about the states in the middle? How do you get that? You have to then make this variable, right? But these capacitors have a Cmin to Cmax, right? So then your open doesn't look like an open. Your open looks like 1 over omega C1 min, right? That's your open. You can increase and try to get closer to a short because this is 1 over omega C1 max. But if I try to push this over here, I will end up moving this over here, right? Because in integrated varactors or even switch capacitors, however you build them, there is a ratio of Cmax to Cmin, right? And this Cmax to Cmin ratio at a certain frequency is sort of constant.
What I'm asking is, can we remove the total varactor itself and replace it with the open and the short?
But then you will only get two states, right? What about the other states? And when you replace it with the open or short, in order to get a good short, you want this R to be small. So you'll put a big switch. And when you put the bit switch, that switch will have a C off capacitance. So you'll again be not at a open, you'll be somewhere here in the Smith chart, right? And that will only give you two states. So now in order to get more states, I can cascade multiple RTPSs, but then I have an area problem that I have a really big area phase shifter. And if I am cascading, then I might as well, to make an apples to apples comparison, I might as well just introduce some more states inside each one so that I don't have to cascade that many designs. But it is true that in order to get a 0 or 180 degree phase shift, a coarse discrete phase shift, I can put this and then just have a switch over here, right? And when this switch is on 0, I'll get an open reflection, right? So gamma t will be I guess minus 1, right? And when I put a short, it will be 1. Is that what? No. Sorry, minus 1 when it's open, 1 when it's short, right? That's correct. Yeah. Yeah. So, oh no, yeah, sorry, what I'm saying, plus 1 when it's open, minus 1 when it's short. Sorry. So, this is one approach, and then we will just consider another the last passive phase shifter that we are going to talk about, which is just a loaded transmission line, right? So we already saw with a we already saw with a slow wave that I can adjust the velocity of the transmission line by changing the phase. So the idea is that I have my let's say I have my GSG, right? And then what I have is an inductance, right? And what I'm trying to do is add some capacitance with a switch, right? To my line, right? And when I have multiple of these, right? I'm just changing the capacitance of the switch. So I'm basically changing the square root of LC product, right? Beta was square root of LC, or that's the delay through the line delay is square root of LC, right? So the delay is square root LC, right? But my problem is that the Z naught is square root of L over C, right? So if I change the delay by adding C, I'm changing my impedance down, right? So then I have to find some way that when I am increasing C, I'm also increasing L so that I keep my impedance constant, right? That's basically the approach. So what they effectively try to do here is create something a little complex, right? But we'll just see how it works. So they have this line which I will call G2. Then I have another line which I call G1, right? And then I have my signal line which I'll just draw in a different color. And then I have G1. And then I have G2, right? So then the idea is that I also have switches, right, that basically short this particular line as well, right, to the ground underneath. Right? So I have switches that short this line, and this ground itself, I shouldn't draw it as a continuous line, right? So this ground itself has strips over here, right? So I am enabling, so if I have another strip over here like so, okay, let's draw the strips below in green, right? And then I'm having switches that connect to this from this line down to this strip as well, right? So I'm creating modes of operation where either I have a situation where I have a SG1 G1 or a situation where I have a SG2 G2, right? So I'm basically trying to add, in addition to the capacitance switches, I'm adding these switches as well. So using this approach, I can try to keep my impedance constant when my load is changing, right? And I've added the reference, and you can take a look at this paper, but effectively through that approach, they are able to achieve a fairly uniform, like 5-bit, a bit even more than phase variations, right? And they did 0 to 180 degrees. And the S21 is pretty uniform, right? Which, if the impedance was changing throughout the line, then it would not be so uniform. But by adjusting the L when the C changes, right, they're able to accommodate both a change in phase shift and keep the impedance constant while loading the transmission line. Let's actually draw maybe I'll translate this view to this view and to the vertical view. So this is their central signal trace, right? And in the below the central signal trace, they have capacitive strips, right? And this capacitive strip is shorted to ground, right? And this is what they call the S switch, right? And then this is what I called the G1, right? And that switch over here is connected closely to the L switches, right? And actually, I mean, I should, I think, to keep their notation correct, this is the C switch, right? And they also have additional switches, right, which exist in between this to this, like a resistive load, which they call the S switch. Okay, so these are the three sets of switches that they have, right? So what you're saying is that when you change there is a L and C, let's say that I keep adding capacitances, right? So gradually my Z naught is varying, right? But I'm willing to accept a certain variation in Z naught because the mismatch is acceptable to me and I'm getting a certain phase variation square root of LC, right? But at some point, I have changed the C so much that the impedance has changed a lot, right? So then at that point, I'd like to introduce a change in L as well to shift the inductance back, right? So what you're basically doing is when, as they enable these C switches, they are increasing this C, right? So the impedance is dropping, right? And then, so imagine that they start in this state with the L switches enabled, right? And they are increasing the C switches and the impedance is dropping. Then at some point, they disable this L. So now this ground plane goes away and you have G2 switches, G2 becomes your ground, right? So at that point, the L has also gone up, right? And your C is, you can go back to your first C or you can start from a middle C and then again vary. So it is not that at every state you're keeping the impedance perfectly constant. It is that you are willing to accept a certain level of mismatch and get for the phase variations that you get, right? And this of course also depends on how many such strips that you have, right? Because you have these C's, you have multiple of these C's, right? Which are located at different points along the chain. And what they find is that depending upon these states, the loss starts varying. So in order to equalize the loss, they introduce this S switch, which is basically saying that I'll make the L coarse variable, I'll make the C more fine variable, but I will also take this part and make this variable periodically, right? So that way I'll keep my loss uniform, I'll get my phase shift and I'll get my impedance uniform, right? So that's basically why in that measurement that they show, there is these S bits, right? If you keep all the S bits off, right, this is their loss profile. If you keep all the S bits on, this is their loss profile. And then they are trying to keep it uniform. So then as they change their phase shifter code, they are basically adapting the S bits to keep it in the middle, right? So you can also see that it's I mean, in terms of area, it is small, though it has a dimension on one side which is pretty long, right? But you could, conceptually break it and split it into two phase shifters that loop back among each other to keep the area, like, meander this whole line and then do it, right? So one of the things that they have in this paper also is that they look at how the phase shifter behaves across multiple samples of the chip, right? And their observation is that this is a fairly uniform phase shifter. So that fairly uniform across process phase shifter, that's sensitive to PVT, right? But even in this approach, it requires a hybrid approach because you're starting with 180 degrees. So you have 40 codes across 180 degrees. So technically, you could think that you have a resolution of 180 over 40, right? So something that is of the order of a few degrees, right? But the phase shifts are pretty precise and repeatable across process, right? That's so this forms a part of a very large chip that this group published. And other people have also built loaded T lines, but effectively the approach effectively stays the same, which is that you have your signal in some way, and then you have another metal next to it, and you ground the metal or you open the metal out to effectively shift the inductance of your signal line so that you can keep your impedance constant as you vary the phase. So that's broadly that's what you have to do. There's really no other magic here. So one thing to note in phase shifters or in passive phase shifters generally is that all passive phase shifters try to equalize losses, right? So if you generally, if I make a plot, right, which is insertion loss across phase shift, right? Let's say that my curve looks something like this. For example, this is a typical RTPS response, right? Then sorry, it should look the other way because I'm doing loss, right? So it should look the other way, right? Where the loss is higher at some point. Then what I have to do is I have to design to this point, right? So because sure I have low loss in this state, but my phase shifter wants to see uniform loss, right? So I have to artificially increase my loss here now, right? So, and similarly increase my loss here. So my phase shifter performance is limited by the maximum loss state that I have, right? So when I'm trying to optimize my phase shifter design, I should try to, because I can always find ways to introduce additional loss, right? But so what I should try to do is try to see if I can get curves that are, for example, flatter this way, right? If this sort of curve may be more preferable because my worst case loss is less, and on this side I now have to compensate for the loss and increase my loss to get a uniform response. But then my phase shifter will have lower loss overall because I am able to design that. So always have to design for worst case loss, not best case loss in the phase shifter.